We are moving ahead to section 4.4. I find that this section, and I'll read that name to you in a moment, I find that this section fits much better at this point in the course than what the author decided to do and putting it in chapter 4. So, just kind of give you guys a little bit bigger picture. Chapter 4 is where we get into the heavier applications of derivatives. And, in a sense, it makes sense that this section, this topic would fit there. But I find that it really fits much better in with the chapter 3 things. I also take some of the topics that our book has in chapter 3 and I move them into that like chapter 4 discussion. So I do a little mixing around. I've been teaching this course for a long time. I feel it flows much easier this way. So okay, so that's why we're going to 4.4 right now. What is this? It's called L'Hopital's rule. So the S here, it looks like La Hospital's rule, right? The S here is silent. L'Hôpital. The guy's French, so there you go. And there's the pronunciation down at the bottom, L'Hôpital. Kind of an interesting story with L'Hôpital. So turns out, I'll just tell you this real quick, the rule that we're going to learn, it actually applies to limits. So we're going to be able to tackle some limits that we would not have been able to do before. The kind of the story goes, L'Hôpital was a wealthy French guy. He got out of the French military when he was, maybe in his early to mid 20s. And, he's from this very, very wealthy family. What's he going to do with the rest of his life? And so he decides to dedicate himself to studying mathematics. It was a very serious hobby of his, and not something that anybody's going to learn in school. He lived in the 1700s when calculus was just becoming, had only been around maybe 50 or so years, and not a lot of people knew about it. So it was the cutting edge stuff in Europe at that time, and so he hired a guy named Jacob Bernoulli to come and teach him calculus. Okay, so Jacob Bernoulli, this is just what he did. This is how he made his money. He did his own thing. He did his own mathematical discoveries, but then he would go around and teach these rich guys the latest math techniques, and he made a lot of money that way. So here's how the story goes. When L'Hopital hired Bernoulli, part of their contract was anything Bernoulli shared with him was L'Hopital's property. Okay, like he was purchasing these mathematical ideas. So the rule you're going to see was actually developed by Jacob Bernoulli. Uh, he's the one who discovered it. He shared it with L'Hopital, and L'Hopital claimed it as his property. Years later, L'Hopital would be the author of the first calculus textbook, putting everything together that he learned. And when this rule came up, he called it by his own name. He called it L'Hopital's rule. Fair and square. He bought it. He didn't discover it, but he bought it. It's all legal. And so that's it. It's L'Hopital's rule. So Bernoulli was not happy with that. There's more to the story, but I'll leave it. Okay. So what is L'Hopital's rule? Like I said, it's about taking limits. Let's take a look. I've got 3 here at the beginning that, okay, so we'll see what happens. All right, so how about limit as x approaches infinity of the function e to the x over 2x? And say, okay, well, what's the big deal? We did limits that had e. We did, infinite limits at infinity, or excuse me, infinite limits where x approached infinity, right? We did that sort of thing. Okay, but this situation, just the way it comes together, right? So if you think of the parts individually, the numerator is going to infinity as x gets larger, and the denominator is going to infinity as x gets larger. So I've got that right over here. Plugging this in gives infinity over infinity. Okay, and we do not have an answer to that. All right, we saw this situation before, but it was always with polynomials, right? there'd be a way we could rewrite, that original expression where we could maybe divide everything by the same power of x or something. And we could get our way around this. But that's definitely not the case here. We cannot simplify that or rewrite it in any way. We're kind of stuck. And so here's kind of the picture. Everything in this section, it's all about infinity. Really what calculus is, and if you wanted to describe calculus to somebody, like what is calculus all about in just a couple words, you would be correct in saying it's really a study of infinity. Okay, ratios of infinity like we have here. Okay, here's a good way to think of this situation. The numerator, the e to the x, right? Because it's in the numerator, that's pulling the value of this limit to infinity, right? The numerator, it goes with the numerator, right? It's pulling it to infinity. The denominator, though, it's always doing the opposite, like the reciprocal. So as the denominator gets bigger, that's actually pulling the whole thing to 0. Okay, so we saw cases where we had maybe like a limit where we had a number divided by infinity. Well, if the denominator is getting bigger, then the whole thing is going towards 0. Okay, so the numerator is pulling it in one direction. The denominator is pulling it in the other direction. Who's going to win? So infinities are not created equal. So really when we write this infinity, it's a bit deceiving. Sure, they both keep increasing, but they don't do that at the same speed or maybe the same rate. Maybe e to the x is moving to infinity faster than 2x moves to infinity, right? Or maybe 2x goes to infinity faster than e to the x. And so it's like, who is really moving faster? That's who wins. Okay, so we'll get back to this example after I show you the rule. Here's the next situation. We'll look at this example along the way too. The limit as x approaches 0 from the right of x times the natural log of x. All right. Approaching 0 from the right. So if we were to plug in, well, this x would just become the 0. And as we look at the limit as x approaches 0 from the right of natural log x, if you recall the graph of a log, as you approach 0 from the right, it goes down, down, with its vertical asymptote. So this portion of it is going to negative infinity. And who's going to win? Does 0 win or does negative infinity win? And you might be tempted to guess, well, 0 times anything is 0. So what's the problem? The problem with that is when we write the 0 and negative infinity, the truth is the value never actually reaches 0, right? We're approaching 0, but we never actually get there. Just the same as we approach negative infinity, we never actually get there. So we've got numbers getting smaller and smaller and smaller, headed towards 0, being multiplied by bigger and bigger and bigger negative numbers. Okay, so who's going to win? Like, are these numbers headed towards 0 faster than these numbers head to negative infinity? Or maybe these head to negative infinity faster than these head towards 0? Sometimes it's shocking, and there's like a balance even. Like they'll pull. It's like a tug of war, right? They're pulling, and it'll like balance out somewhere in the middle. So maybe 0 will win, maybe negative infinity will win, or maybe it's actually something in between. Okay, I got one more example before we get into what the rule is. How about this? The limit as x approaches 0, the sine of x raised to the x. Okay, wow. So if we think about plugging in, well, the sine of 0 is 0. And we're raising to the x, so that's simply we're raising to the 0. Okay, why is this one? Why don't we know the answer to this one? Well, okay, so down here we're approaching 0, so our numbers are getting smaller. Same thing here. These numbers are getting smaller. The 0 here is pulling the answer for the limit towards 0. The 0 here is pulling the answer to the limit towards 1, right? Anything raised to the 0 equals 1. So now it's not pulling necessarily to infinity, but this answer is either 0, or maybe it's 1, or maybe it's somewhere in between. Okay. This has been a fantastic introduction. Really, the concept here is big. That we don't actually get to 0 itself, because it's tempting to answer a lot of these. It's about the tug of war that's going on as we get closer to 0. Okay, so let's get to the rule. First, we need to define, these forms that we've seen, 0 to the 0 and the infinities. We call them indeterminate forms. So I'll just show you this definition here. A limit, let's read the whole thing. The indeterminate form of a limit. Okay. And just that name, indeterminate, we don't know the answer. We cannot determine what the answer to this limit is. Okay. It's a limit that after simplification results in one of these cases. So it could be infinity over infinity. We saw that a moment ago. There could be a negative infinity over infinity, right? That's no better. 0 over 0. If it's already been simplified, then that's indeterminate. We saw this case, obviously we did this a ton in chapter 2. We had 0 over 0, but we were always able to simplify. Factor and cancel or conjugate or whatever. So we're saying even after simplification, you still have 0 over 0. Then you're stuck, right? Okay. Maybe 0 times infinity, right? The tug of war. Who will win? You could throw a negative in there. 0 times negative infinity. Here's an interesting one. Infinity minus infinity. Right? 1's going to infinity, right? This is pulling it to infinity. This is pulling it to negative infinity. So when you subtract, it will depend on which one is going to infinity faster. And there's still that tug of war happening. Okay. And maybe the answer is somewhere in the middle. Infinity raised to the 0. All right, we've got these three. These last ones have the exponents. So infinity raised to the 0. Okay, this would be pulling it to infinity. This 0 would be pulling it to 1. 0 to the 0, we talked about that. Pulling it to 0, pulling it to 1. Or 1 to the infinity. Well, as you approach 1, that's pulling the answer to 1. Right? 1 to anything equals 1. But the infinity here is pulling it to infinity. Right? Again, you never actually reach 1. So there's the tug going there. All right. Let's do our first example. I think we can squeeze that into this. Oh, I got to tell you the rule. Oh my gosh. Talked about indeterminate forms. Okay, you know what? Let's stop this video here because it's just we're just gonna go way over. So we defined the indeterminate forms. You get to see L'Hopital's rule in the next one.